Operational amplifier.
An operational amplifier is a DC-coupled high-gain electronic voltage amplifier with a differential input and, usually, a single-ended output. In this configuration, an op-amp produces an output potential that is typically hundreds of thousands of times larger than the potential difference between its input terminals. Operational amplifiers had their origins in analog computers, where they were used to do mathematical operations in many linear, non-linear and frequency-dependent circuits. Characteristics of a circuit using an op-amp are set by external components with little dependence on temperature changes or manufacturing variations in the op-amp itself, which makes op-amps popular building blocks for circuit design. Op-amps are among the most widely used electronic devices today, being used in a vast array of consumer, industrial, and scientific devices. Many standard IC op-amps cost only a few cents in moderate production volume. However, some integrated or hybrid operational amplifiers with special performance specifications may cost over $100 in small quantities. Op-amps may be packaged as components, or used as elements of more complex integrated circuits. The op-amp is one type of differential amplifier. Other types of differential amplifier include the fully differential amplifier, similar to the op-amp, but with two outputs, the instrumentation amplifier, usually built from three op-amps, the isolation amplifier, similar to the instrumentation amplifier, but with tolerance to common mode voltages that would destroy an ordinary op-amp, and negative feedback amplifier, usually built from one or more op-amps and a resistive feedback network.
Circuit notation.
The circuit symbol for an op-amp is shown to the right, where V plus non-inverting input, V. Inverting input, VOUT, output, versus plus positive power supply, versus negative power supply. The power supply pins, versus plus and versus, can be labeled in different ways, CIC power supply pins. Often these pins are left out of the diagram for clarity, and the power configuration is described or assumed from the circuit.
Operation.
The amplifier's differential inputs consist of a non-inverting input, plus with voltage V plus and an inverting input, with voltage V. Ideally the op-amp amplifies only the difference in voltage between the two, which is called the differential input voltage. The output voltage of the op-amp VOUT is given by the equation. Where AOL is the open-loop gain of the amplifier, the term open loop refers to the absence of a feedback loop from the output to the input.
Open loop.
The magnitude of AOL is typically very large, 100,000 or more for integrated circuit op-amps, and therefore even a quite small difference between V plus and V drives the amplifier output nearly to the supply voltage. Situations in which the output voltage is equal to or greater than the supply voltage are referred to as saturation of the amplifier. The magnitude of AOL is not well controlled by the manufacturing process, and so it is impractical to use an operational amplifier as a standalone differential amplifier. Without negative feedback, and perhaps with positive feedback for regeneration, an op-amp acts as a comparator. If the inverting input is held at ground, 0V, directly or by a resistor G, and the input voltage fan applied to the non-inverting input is positive, the output will be maximum positive. If fan is negative, the output will be maximum negative. Since there is no feedback from the output to either input, this is an open-loop circuit acting as a comparator. The circuit's gain is just the AOL of the op-amp.
Closed loop.
If predictable operation is desired, negative feedback is used, by applying a portion of the output voltage to the inverting input. The closed-loop feedback greatly reduces the gain of the circuit. When negative feedback is used, the circuit's overall gain and response becomes determined mostly by the feedback network, rather than by the op-amp characteristics. If the feedback network is made of components with values small relative to the op-amp's input impedance, the value of the op-amp's open-loop response AOL does not seriously affect the circuit's performance. The response of the op-amp circuit with its input, output, and feedback circuits to an input is characterized mathematically by a transfer function. Designing an op-amp circuit to have a desired transfer function is in the realm of electrical engineering. The transfer functions are important in most applications of op-amps, such as in analog computers. High input impedance at the input terminals and low output impedance at the output terminal, S, are particularly useful features of an op-amp. In the non-inverting amplifier on the right, the presence of negative feedback via the voltage divider RF, RG determines the closed-loop gain ACL equals Vout/Van. Equilibrium will be established when Vout is just sufficient to reach around and pull the inverting input to the same voltage as Van. The voltage gain of the entire circuit is thus 1 plus RF RG. As a simple example, if Van equals 1V and RF equals RG, Vout will be 2V, exactly the amount required to keep V at 1V. Because of the feedback provided by the RF, RG network, this is a closed-loop circuit. Another way to analyze this circuit proceeds by making the following, usually valid, assumptions. When an op-amp operates in linear, that is, not saturated, mode, the difference in voltage between the non-inverting, plus pin and the inverting pin is negligibly small, the input's impedance between, plus and pins is much larger than other resistances in the circuit. The input signal Van appears at both, plus and pins, resulting in a current I through RG equal to Van RG. Since Kirchhoff's current law states that the same current must leave a node as enter it, and since the impedance into the pin is near infinity, we can assume practically all of the same current I flows through RF, creating an output voltage. By combining terms, we determine the closed-loop gain ACL.
Op-amp characteristics. Ideal op-amps.
An ideal op-amp is usually considered to have the following properties. Infinite open-loop gain G equals Vout/Van, infinite inputs impedance RIN, and so zero input current, zero input offset voltage, infinite voltage range available at the output, infinite bandwidth with zero phase shift and infinite slew rate, zero outputs impedance route, zero noise, infinite common mode rejection ratio, CMRR, infinite power supply rejection ratio. These ideals can be summarized by the two golden rules. The first rule only applies in the usual case where the op-amp is used in a closed-loop design, negative feedback, where there is a signal path of some sort feeding back from the output to the inverting input. These rules are commonly used as a good first approximation for analyzing or designing op-amp circuits 177. None of these ideals can be perfectly realized. A real op-amp may be modeled with non-infinite or non-zero parameters using equivalent resistors and capacitors in the op-amp model. The designer can then include these effects into the overall performance of the final circuit. Some parameters may turn out to have negligible effect on the final design while others represent actual limitations of the final performance that must be evaluated.
Real op-amps.
Real op-amps differ from the ideal model in various aspects.
DC imperfections.
Real operational amplifiers suffer from several non-ideal effects.
AC imperfections.
The op-amp gain calculated at DC does not apply at higher frequencies. Thus, for high-speed operation, more sophisticated considerations must be used in an op-amp circuit design. Stability. Associated with the bandwidth limitation is a phase difference between the input signal and the amplifier output that can lead to oscillation in some feedback circuits. For example, a sinusoidal output signal meant to interfere destructively with an input signal of the same frequency will interfere constructively if delayed by 180 degrees, forming positive feedback. In these cases, the feedback circuit can be stabilized by means of frequency compensation, which increases the gain or phase margin of the open-loop circuit. The circuit designer can implement this compensation externally with a separate circuit component. Alternatively, the compensation can be implemented within the operational amplifier with the addition of a dominant pole that sufficiently attenuates the high-frequency gain of the operational amplifier. The location of this pole may be fixed internally by the manufacturer or configured by the circuit designer using methods specific to the op-amp. In general, dominant pole frequency compensation reduces the bandwidth of the op-amp even further. When the desired closed-loop gain is high, op-amp frequency compensation is often not needed because the requisite open-loop gain is sufficiently low. Consequently, applications with high closed-loop gain can make use of op-amps with higher bandwidths, noise, distortion, and other effects. Reduced bandwidth also results in lower amounts of feedback at higher frequencies, producing higher distortion, noise, and output impedance and also reduced output phase linearity as the frequency increases.
Nonlinear imperfections.
In the case of an op-amp using a bipolar power supply, a voltage gain that produces an output that is more positive or more negative than that maximum or minimum. Or, in the case of an op-amp using a single supply voltage, either a voltage gain that produces an output that is more positive than that maximum, or a signal so close to ground that the amplifier's gain is not sufficient to raise it above the lower threshold.
Power considerations.
Modern integrated FET or MOS-FET op-amps approximate more closely the ideal op-amp than bipolar ICs when it comes to input impedance and input bias currents. Bipolars are generally better when it comes to input voltage offset, and often have lower noise. Generally, at room temperature, with a fairly large signal, and limited bandwidth, FET and MOS-FET op-amps now offer better performance.
Internal circuitry of 741 type op-amp.
Sourced by many manufacturers, and in multiple similar products, an example of a bipolar transistor operational amplifier is 741 circuit designed by Dave Fulligar in Fairchild Semiconductor after Bob Widler LM301. In this discussion, we use the parameters of the hybrid pi model to characterize the small signal, grounded emitter characteristics of a transistor. In this model, the current gain of a transistor is denoted HFE, more commonly called the B.
Architecture.
A small-scale integrated circuit, the 741 op-amp shares with most op-amps an internal structure consisting of 3 gain stages. Differential amplifier, outlined blue, provides high differential amplification, gain, with rejection of common mode signal, low noise, high input impedance, and drives a voltage amplifier, outlined magenta, provides high voltage gain, a single pole frequency roll-off, and in turn drives the output amplifier, outlined cyan and green, provides high current gain, low output impedance, along with output current limiting, and output short-circuit protection. Additionally, it contains current mirror, outlined red, bias circuitry and a gain stabilization capacitor, 30 picofarads.
Differential amplifier.
A cascaded differential amplifier followed by a current mirror active load. The input stage, outlined in blue, is a transconductance amplifier, turning a differential voltage signal at the bases of Q1, Q2 into a current signal into the base of Q15. It entails 2 cascaded transistor pairs, satisfying conflicting requirements. The first stage consists of the matched NPN emitter follower pair Q1, Q2 that provide high input impedance. The second is the matched PNP common base pair Q3, Q4 that eliminates the undesirable Miller effect. It drives an active load Q7 plus matched pair Q5, Q6. That active load is implemented as a modified Wilson current mirror. Its role is to convert the differential input current signal to a single-ended signal without the attendant 50% losses, increasing the op-amp's open-loop gain by 3 decibels. Thus, a small signal differential current in Q3 versus Q4 appears summed, doubled, at the base of Q15, the input of the voltage gain stage.
Voltage amplifier.
The Class A voltage gain stage, outlined in magenta, consists of the two NPN transistors Q15/Q19 connected in a Darlington configuration and uses the output side of current mirror Q12/Q13 as its collector, dynamic, load to achieve its high voltage gain. The output sink transistor Q20 receives its base drive from the common collectors of Q15 and Q19. The level shifter Q16 provides base drive for the output source transistor Q14. Note the similarity between the transistors Q15 and Q7. The transistor Q22 prevents this stage from saturating by diverting the excessive Q15 base current. It acts as a Baker clamp.
Output amplifier.
The output stage, Q14, Q20, outlined in cyan, is a Class AB push-pull emitter follower amplifier. It provides an output drive with impedance of 50 ohm, in essence, current gain. Transistor Q16, outlined in green, provides the quiescent current for the output transistors, and Q17 provides output current limiting.
Biasing to circuits.
Provide appropriate quiescent current for each stage of the op-amp. The resistor, 39K, connecting the diode connected, Q11 and Q12, and the given supply voltage, versus plus. Versus. Determine the current in the current mirrors, matched pairs, Q10/Q11 and Q12/Q13. The collector current of Q11, I1139K equals versus plus. Versus. 2 VBE. For the typical versus equals plus minus 20 V, the standing current in Q11/Q12, as well as in Q13, would be 1 mA. A supply current for a typical 741 of about 2 mA agrees with the notion that these two bias currents dominate the quiescent supply current. Transistors Q11 and Q10 form a Whittler current mirror, with quiescent current in Q10 I10 such that Ln, I11/I10, equals I10 5K/28 MV, where 5K represents the emitter resistor of Q10, and 28 MV is Vt, the thermal voltage at room temperature. In this case I10. 20 mA.
Differential amplifier.
The biasing circuit of this stage is set by a feedback loop that forces the collector currents of Q10 and Q9 to nearly match. The small difference in these currents provides the drive for the common base of Q3/Q4. Note that the base drive for input transistors Q1/Q2 is the input bias current and must be sourced externally. The summed quiescent currents of Q1/Q3 plus Q2/Q4 is mirrored from Q8 into Q9, where it is summed with a collector current in Q10, the result being applied to the bases of Q3/Q4. The quiescent currents of Q1/Q3, resp. Q2/Q4, I1 will thus be half of I10, of order 10 mA. Input bias current for the base of Q1, resp. Q2, will amount to I1/B. Typically 15 nA, implying a current gain HFE 200 for Q1, Q2. This feedback circuit tends to draw the common base node of Q3/Q4 to a voltage VCOM 2 VBE, where VCOM is the input common mode voltage. At the same time, the magnitude of the quiescent current is relatively insensitive to the characteristics of the components Q1/Q4, such as HFE, that would otherwise cause temperature dependence or part-to-part variations. Transistor Q7 drives Q5 and Q6 into conduction until their equal collector currents match that of Q1/Q3 and Q2/Q4. The quiescent current in Q7 is VBE/50 K, about 35 mA, as is the quiescent current in Q15, with its matching operating point. Thus, the quiescent currents are pairwise matched in Q1/Q2, Q3/Q4, Q5/Q6, and Q7/Q15.
Voltage amplifier.
Quiescent currents in Q16 and Q19 are set by the current mirror Q12/Q13, which is running at 1 mA. through some mechanism, the collector current in Q19 tracks that standing current.
Output amplifier.
In the circuit involving Q16, variously named rubber diode or VBE multiplier, the 4.5 kΩ resistor must be conducting about 100 MA, with the Q16 VBE roughly 700 MV. Then the VCB must be about 0.45 V and VCE at about 1.0 V. Because the Q16 collector is driven by a current source and the Q16 emitter drives into the Q19 collector current sink, the Q16 transistor establishes a voltage difference between Q14 base and Q20 base of 1 V, regardless of the common mode voltage of Q14/Q20 base. The standing current in Q14/Q20 will be a factory XP, 100 MV/VT. 36 smaller than the 1 mA quiescent current in the Class A portion of the op-amp. This small standing current in the output transistors establishes the output stage in Class AB operation and reduces the crossover distortion of this stage.
Small signal differential mode.
A small differential input voltage signal gives rise, through multiple stages of current amplification, to a much larger voltage signal on output.
Input impedance.
Because Q1 and Q3, resp. Q2 and Q4, form a Darlington pair, the small signal differential input impedance is of order 2 He, where high is the small signal input impedance, common emitter, of Q1 and Q3, resp. Q2 and Q4, and where HFE is the transistor small signal current gain, or B. This contrasts with what would be the case with a simpler emitter-coupled pair, long-tailed pair, input stage, where the differential input impedance is too high, a factor of B lower. A typical 741 op-amp has an input impedance 2 to 8 mO.
Differential amplifier.
A differential voltage band at the op-amp inputs, pins 3 and 2, respectively, gives rise to a small differential current in the bases of Q1 and Q2 ion. Band/2 high HFE. This differential base current causes a change in the differential collector current in each leg by ion HFE. Introducing the transconductance of Q1, Gm equals HFE/high, the small signal current at the base of Q15, the input of the voltage gain stage, is Van Gm/2. This portion of the op-amp cleverly changes a differential signal at the op-amp inputs to a single-ended signal at the base of Q15, and in a way that avoids wastefully discarding the signal in either leg. To see how, notice that a small negative change in voltage at the inverting input, Q2 base, drives it out of conduction, and this incremental decrease in current passes directly from Q4 collector to its emitter, resulting in a decrease in base drive for Q15. On the other hand, a small positive change in voltage at the non-inverting input, Q1 base, drives this transistor into conduction, reflected in an increase in current at the collector of Q3. This current drives Q7 further into conduction, which turns on current mirror Q5/Q6. Thus, the increase in Q3 emitter current is mirrored in an increase in Q6 collector current, resulting also in a decrease in base drive for Q15. Besides avoiding wasting 3 dB of gain here, this technique decreases common mode gain and feed-through of power supply noise.
Voltage amplifier.
A current signal I at Q15's base gives rise to a current in Q19 of order IB2, the product of the HFE of each of Q15 and Q19, which are connected in a Darlington pair. This current signal develops a voltage at the bases of output transistors Q14/Q20 proportional to the high of the respective transistor.
Output amplifier.
Output transistors Q14 and Q20 are each configured as an emitter-follower, so no voltage gain occurs here. Instead, this stage provides current gain, equal to the HFE of Q14, resp. Q20. The output's impedance is not zero, as it would be in an ideal op-amp, but with negative feedback it approaches zero at low frequencies.
Overall open-loop voltage gain.
the net open-loop small signal voltage gain of the op-amp involves the product of the current gain HFE of some 4 transistors. In practice, the voltage gain for a typical 741 style op-amp is of order 200,000, and the current gain, the ratio of input impedance 2. 6 mho to output's impedance 50 ohm, provides yet more power gain.
Other linear characteristics. Small signal common mode gain.
The ideal op-amp has infinite common mode rejection ratio, or zero common mode gain. In the present circuit, if the input voltages change in the same direction, the negative feedback makes Q3/Q4 base voltage follow, with 2 VBE below, the input voltage variations. Now the output part, Q10, of Q10-Q11 current mirror keeps up the common current through Q9/Q8 constant in spite of varying voltage. Q3/Q4 collector currents, and accordingly the output current at the base of Q15, remain unchanged. In the typical 741 op-amp, the common mode rejection ratio is 90 dB, implying an open-loop common mode voltage gain of about 6.
Frequency compensation.
The innovation of the Fairchild Megampere 741 was the introduction of frequency compensation via an on-chip, monolithic, capacitor, simplifying application of the op-amp by eliminating the need for external components for this function. The 30 pF capacitor stabilizes the amplifier via Miller compensation and functions in a manner similar to an op-amp integrator circuit. Also known as dominant pole compensation because it introduces a pole that masks, dominates, the effects of other poles into the open-loop frequency response. In a 741 op-amp this pole can be as low as 10 Hz, where it causes a 3 dB loss of open-loop voltage gain. This internal compensation is provided to achieve unconditional stability of the amplifier in negative feedback configurations where the feedback network is non-reactive and the closed-loop gain is unity or higher. By contrast, amplifiers requiring external compensation, such as the Megampere 748, may require external compensation or closed-loop gain significantly higher than unity.
Input offset voltage.
The offset null pins may be used to place external resistors, typically in the form of the two ends of a potentiometer, with the slider connected to versus and parallel with the emitter resistors of Q5 and Q6, to adjust the balance of the Q5/Q6 current mirror. The potentiometer is adjusted such that the outputs is null, mid-range, when the inputs are shorted together.
Nonlinear characteristics. Input breakdown voltage.
The transistors Q3, Q4 help to increase the reverse VBE rating. The base emitter junctions of the NPN transistors Q1 and Q2 break down at around 7 V, but the PNP transistors Q3 and Q4 have VBE breakdown voltages around 50 V.
Output stage voltage swing and current limiting.
Variations in the quiescent current with temperature, or between parts with the same type number, are common, so crossover distortion and quiescent current may be subject to significant variation. The output range of the amplifier is about 1 volt less than the supply voltage, owing in part to VBE of the output transistors Q14 and Q20. The 25 ohm resistor at the Q14 emitter, along with Q17, acts to limit Q14 current to about 25 MA. Otherwise, Q17 conducts no current. Current limiting for Q20 is performed in the voltage gain stage. Q22 senses the voltage across Q19's emitter resistor, 50 ohm. As it turns on, it diminishes the drive current to Q15 base. Later versions of this amplifier schematic may show a somewhat different method of output current limiting.
Applicability considerations.
Note: while the 741 was historically used in audio and other sensitive equipment, such use is now rare because of the improved noise performance of more modern op-amps. Apart from generating noticeable hiss, 741s and other older op-amps may have poor common mode rejection ratios and so will often introduce cable-borne mains hum and other common mode interference, such as switch clicks, into sensitive equipment. The 741 has come to often mean a generic op-amp IC, such as Megampere 741, LM301, 558, LM324, TBA221, or a more modern replacement such as the TL071. The description of the 741 output stage is qualitatively similar for many other designs, that may have quite different input stages, except some devices, Megampere 748, LM301, LM308, are not internally compensated, require an external capacitor from output to some point within the operational amplifier, if used in low closed-loop gain applications. Some modern devices have rail-to-rail output capability, meaning that the output can range from within a few millivolts of the positive supply voltage to within a few millivolts of the negative supply voltage.
Classification.
Op-amps may be classified by their construction. Discrete, built from individual transistors or tubes valves. IC, fabricated in an integrated circuit, most common. Hybrid. IC op-amps may be classified in many ways, including military, industrial, or commercial grade. For example, the LM301 is the commercial grade version of the LM101, the LM201 is the industrial version. This may define operating temperature ranges and other environmental or quality factors. Classification by package type may also affect environmental hardiness, as well as manufacturing options. DIP, and other through-hole packages are tending to be replaced by surface mount devices. Classification by internal compensation, op-amps may suffer from high-frequency instability in some negative feedback circuits unless a small compensation capacitor modifies the phase and frequency responses. Op-amps with a built-in capacitor are termed compensated, or perhaps compensated for closed-loop gains down to, say, 5. All others are considered uncompensated. Single, dual and quad versions of many commercial op-amp IC are available, meaning 1, 2 or 4 operational amplifiers are included in the same package. Rail-to-rail input, and/or output, op-amps can work with input, and/or output, signals very close to the power supply rails. CMOS op-amps, such as the California 3140E, provide extremely high input resistances, higher than JFET input op-amps, which are normally higher than bipolar input op-amps. Other varieties of op-amp include programmable op-amps, simply meaning the quiescent current, gain, bandwidth and so on can be adjusted slightly by an external resistor. Manufacturers often tabulate their op-amps according to purpose, such as low-noise preamplifiers, wide bandwidth amplifiers, and so on.
Applications. Use in electronic system design.
The use of op-amps as circuit blocks is much easier and clearer than specifying all their individual circuit elements, transistors, resistors, etc., whether the amplifiers used are integrated or discrete. In the first approximation, op-amps can be used as if they were ideal differential gain blocks. At a later stage, limits can be placed on the acceptable range of parameters for each op-amp. Circuit design follows the same lines for all electronic circuits. A specification is drawn up governing what the circuit is required to do, with allowable limits. For example, the gain may be required to be 100 times, with a tolerance of 5% but drift of less than 1% in a specified temperature range. The input's impedance not less than 1 megohm, etc. A basic circuit is designed, often with the help of circuit modeling, on a computer. Specific commercially available op-amps and other components are then chosen that meet the design criteria within the specified tolerances at acceptable cost. If not all criteria can be met, the specification may need to be modified. A prototype is then built and tested. Changes to meet or improve the specification, alter functionality, or reduce the cost, may be made.
Applications without using any feedback.
That is, the op-amp is being used as a voltage comparator. Note that a device designed primarily as a comparator may be better if, for instance, speed is important or a wide range of input voltages may be found, since such devices can quickly recover from full on or full off, saturated states. A voltage level detector can be obtained if a reference voltage VOF is applied to one of the op-amp's inputs. This means that the op-amp is set up as a comparator to detect a positive voltage. If the voltage to be sensed, i.e., is applied to op-amp's plus input, the result is a non-inverting positive level detector. When I is above RF, VO equals plus VSAT. When I is below RF, VO equals VSAT. If I is applied to the inverting input, the circuit is an inverting positive level detector. When I is above RF, VO equals VSAT. A zero voltage level detector, I equals 0, can convert, for example, the output of a sine wave from a function generator into a variable frequency square wave. If I is a sine wave, triangular wave, or wave of any other shape that is symmetrical around 0, the zero-crossing detector's output will be square. Zero-crossing detection may also be useful in triggering TRIACs at the best time to reduce mains interference and current spikes.
Positive feedback applications.
Another typical configuration of op-amps is with positive feedback, which takes a fraction of the output signal back to the non-inverting input. An important application of it is the comparator with hysteresis, the Schmitt trigger. Some circuits may use positive feedback and negative feedback around the same amplifier, for example triangle wave oscillators and active filters. Because of the wide slew range and lack of positive feedback, the response of all the open-loop level detectors described above will be relatively slow. External overall positive feedback may be applied but, unlike internal positive feedback that may be applied within the latter stages of a purpose-designed comparator, this markedly affects the accuracy of the zero-crossing detection point. Using a general-purpose op-amp, for example, the frequency of I for the sine-to-square wave converter should probably be below 100 Hz.
Negative feedback applications. Non-inverting amplifier.
In a non-inverting amplifier, the output voltage changes in the same direction as the input voltage. The gain equation for the op-amp is. However, in this circuit V is a function of out because of the negative feedback through the A1 A2 network. A1 and A2 form a voltage divider, and as V is a high impedance input, it does not load it appreciably. Consequently, where substituting this into the gain equation, we obtain solving for if is very large, this simplifies to. Note that the non-inverting input of the operational amplifier will need a path for DC to ground. If the signal source might not give this, or if that source requires a given load impedance, the circuit will require another resistor, from input to ground. In either case, the ideal value for the feedback resistors, to give minimum offset voltage, will be such that the two resistances in parallel roughly equal the resistance to ground at the non-inverting input pin.
Inverting amplifier.
In an inverting amplifier, the output voltage changes in an opposite direction to the input voltage. As with the non-inverting amplifier, we start with the gain equation of the op-amp. This time, V is a function of both out and van due to the voltage divider formed by RF and RIN. Again, the op-amp input does not apply an appreciable load, so substituting this into the gain equation and solving for if is very large, this simplifies to a resistor is often inserted between the non-inverting input and ground, so both inputs see similar resistances, reducing the input offset voltage due to different voltage drops due to bias current, and may reduce distortion in some op-amps. A DC blocking capacitor may be inserted in series with the input resistor when a frequency response down to DC is not needed and any DC voltage on the inputs is unwanted. That is, the capacitive component of the input's impedance inserts a DC 0 and a low-frequency pole that gives the circuit a bandpass or high-pass characteristic. The potentials at the operational amplifier inputs remain virtually constant, near ground, in the inverting configuration. The constant operating potential typically results in distortion levels that are lower than those attainable with a non-inverting topology.
Other applications.
Audio and video frequency preamplifiers and buffers, differential amplifiers, differentiators and integrators, filters, precision rectifiers, precision peak detectors, voltage and current regulators, analog calculators, analog to digital converters, digital to analog converters, voltage clamping, oscillators and waveform generators. Most single, dual and quad op-amps available have a standardized pinout which permits one type to be substituted for another without wiring changes. A specific op-amp may be chosen for its open-loop gain, bandwidth, noise performance, input impedance, power consumption, or a compromise between any of these factors.
Historical timeline.
1941, a vacuum tube op-amp. An op-amp, defined as a general-purpose, DC-coupled, high-gain, inverting feedback amplifier, is first found in U.S. Patent 2,401,779 summing amplifier filed by Carl D. Swartzel Jr. of Bell Labs in 1941. This design used 3 vacuum tubes to achieve a gain of 90 decibels and operated on voltage rails of ±350 V. It had a single inverting input rather than differential inverting and non-inverting inputs, as are common in today's op-amps. Throughout World War II, Swartzel's design proved its value by being liberally used in the M9 artillery director designed at Bell Labs. This artillery director worked with the 584-seat Louis Rupees radar system to achieve extraordinary hit rates, near 90% that would not have been possible otherwise. 1947, an op-amp with an explicit non-inverting input. In 1947, the operational amplifier was first formally defined and named in a paper by Professor John Aragazni of Columbia University. In this same paper a footnote mentioned an op-amp designed by a student that would turn out to be quite significant. This op-amp, designed by Louis B. Julie, was superior in a variety of ways. It had 2 major innovations. Its input stage used a long-tailed triode pair with loads matched to reduce drift in the output and, far more importantly, it was the first op-amp designed to have 2 inputs, one inverting, the other non-inverting. The differential input made a whole range of new functionality possible, but it would not be used for a long time due to the rise of the chopper-stabilized amplifier. 1949, a chopper-stabilized op-amp. In 1949, Edwin A. Goldberg designed a chopper-stabilized op-amp. This setup uses a normal op-amp with an additional AC amplifier that goes alongside the op-amp. The chopper gets an AC signal from DC by switching between the DC voltage and ground at a fast rate, 60 Hz or 400 Hz. This signal is then amplified, rectified, filtered and fed into the op-amp's non-inverting input. This vastly improved the gain of the op-amp while significantly reducing the output drift and DC offset. Unfortunately, any design that used a chopper couldn't use their non-inverting input for any other purpose. Nevertheless, the much improved characteristics of the chopper-stabilized op-amp made it the dominant way to use op-amps. Techniques that used the non-inverting input regularly would not be very popular until the 1960s when op-amp ICs started to show up in the field. 1953, a commercially available op-amp. In 1953, vacuum tube op-amps became commercially available with the release of the Model K2W from George A. Philbrick Researches, Incorporated. The designation on the devices shown, GAP-R, is an acronym for the complete company name. 2 9-pin 12AX7 vacuum tubes were mounted in an octal package and had a Model K2P chopper add-on available that would effectively use up the non-inverting input. This op-amp was based on a descendant of Louis B. Julie's 1947 design and, along with its successors, would start the widespread use of op-amps in industry. 1961, a discrete IC op-amp. With the birth of the transistor in 1947, and the silicon transistor in 1954, the concept of ICs became a reality. The introduction of the planar process in 1959 made transistors and ICs stable enough to be commercially useful. By 1961, solid-state, discrete op-amps were being produced. These op-amps were effectively small circuit boards with packages such as edge connectors. They usually had hand-selected resistors in order to improve things such as voltage offset and drift. The P45, 1961, had a gain of 94 decibels and ran on ±15 V rails. It was intended to deal with signals in the range of ±10 V. 1961, a varactor bridge op-amp. There have been many different directions taken in op-amp design. Varactor bridge op-amps started to be produced in the early 1960s. They were designed to have extremely small input current and are still amongst the best op-amps available in terms of common mode rejection, with the ability to correctly deal with hundreds of volts at their inputs. 1962, an op-amp in a potted module. By 1962, several companies were producing modular potted packages that could be plugged into printed circuit boards. These packages were crucially important as they made the operational amplifier into a single black box which could be easily treated as a component in a larger circuit. 1963, a monolithic IC op-amp. In 1963, the first monolithic IC op-amp, the Megampere 702 designed by Bob Widler at Fairchild Semiconductor, was released. Monolithic ICs consist of a single chip as opposed to a chip in discrete parts, a discrete IC, or multiple chips bonded and connected on a circuit board, a hybrid IC. Almost all modern op-amps are monolithic ICs. However, this first IC did not meet with much success. Issues such as an uneven supply voltage, low gain and a small dynamic range held off the dominance of monolithic op-amps until 1965 when the Megampere 709, also designed by Bob Widler, was released. 1968, release of the Megampere 741. The popularity of monolithic op-amps was further improved upon the release of the LM101 in 1967, which solved a variety of issues, and the subsequent release of the Megampere 741 in 1968. The Megampere 741 was extremely similar to the LM101 except that Fairchild's facilities allowed them to include a 30 pF compensation capacitor inside the chip instead of requiring external compensation. This simple difference has made the 741 the canonical op-amp, and many modern amps base their pin-out on the 741s. The Megampere 741 is still in production, and has become ubiquitous in electronics. Many manufacturers produce a version of this classic chip, recognizable by part numbers containing 741. The same part is manufactured by several companies. 1970, first high-speed, low-input current FET design. In the 1970s, high-speed, low-input current design started to be made by using FETs. These would be largely replaced by op-amps made with MOS FETs in the 1980s. During the 1970s, single-sided supply op-amps also became available. 1972, single-sided supply op-amps being produced. A single-sided supply op-amp is one where the input and output voltages can be as low as the negative power supply voltage instead of needing to be at least 2 volts above it. The result is that it can operate in many applications with the negative supply pin on the op-amp being connected to the signal ground, thus eliminating the need for a separate negative power supply. The LM324, released in 1972, was one such op-amp that came in a quad package, 4 separate op-amps in one package, and became an industry standard. In addition to packaging multiple op-amps in a single package, the 1970s also saw the birth of op-amps in hybrid packages. These op-amps were generally improved versions of existing monolithic op-amps. As the properties of monolithic op-amps improved, the more complex hybrid ICs were quickly relegated to systems that are required to have extremely long service lives or other specialty systems. Recent trends. Recently, supply voltages in analog circuits have decreased, as they have in digital logic, and low-voltage op-amps have been introduced reflecting this. Supplies of ±5 V and increasingly 3.3 V, sometimes as low as 1.8 V, are common. To maximize the signal range, modern op-amps commonly have rail-to-rail output. The output signal can range from the lowest supply voltage to the highest, and sometimes rail-to-rail input.